Princeton on Anomalies and Nonsupersymmetric D-Branes.
Well, thank you, and thanks to the organizers for putting this conference together so that we can all celebrate Martin's birthday. And I'm very pleased to have the chance to come here and assist in this celebration. So happy birthday, Martin, regardless of which birthday it is. So, well, the most familiar D-branes in string theory are the supersymmetric ones, which are of even or odd dimension, whether we're doing type 2a or type 2b, and they're of dimension 4n plus 1 for type 1. But almost 20 years ago, Ashok Sen showed that there are also non-supersymmetric branes of other dimensions, including for type 2, there are branes of the opposite to usual type, and for type 1, there are a variety of non-supersymmetric branes. The most important examples are for type 1, where Ashok explains that some aspects of heterotic type 1 duality could be better understood if you know about these particular non-supersymmetric branes. So Sen's rules in constructing non-supersymmetric branes were perfectly clear, but a little mysterious. And today I'm going to revisit the discussion and organize it around a certain mod 2 anomaly that explains many properties of these branes. And for those who are not string theorists and are not familiar with anything on my first slide, I do have a bit of good news, which is that for most of this talk, we'll just be discussing this mod 2 anomaly. And then we'll get to the string theory and the branes at the end. And another, well, bit of good or bad news, depending on your perspective, is that the mod 2 anomaly in question is the same one that enters the Kitaev spin chain without time reversal symmetry. So some of you would know many aspects of what I'll say under that, in that context. One more thing I should say is that the same anomaly entered a recent paper I wrote with Robert Dijkgraaf on a subject that superficially has only a very loose relationship to this one. So I'll describe three things that all have the same mod 2 anomaly. Mod 2 anomaly means it'll affect the sign of the path integral or the partition function. So it's mod 2 because you only care about minus signs mod 2. And since when you have three things that all have the same mod 2 anomaly, you have various options for anomaly cancellation. Any two of the three will cancel the anomaly in a non-trivial way, and we'll use all of them in constructing non-supersymmetric branes. And there's a fourth thing that has the same anomaly that was important in my paper with Robert, so there are more options, but we're only going to have three of them today. Now, the most simple anomalous theory we're going to discuss is a theory in one space-time dimension. In other words, space is a point. The only space-time dimension is time, with a single real fermion lambda. And here's the action. This is what the Dirac action reduces to if the space-time dimension is 1. We don't have to, there's no such thing as lambda bar. Lambda is a one-component real fermion. So the action is as simple as I wrote. And I claim that this theory is anomalous, that there's a problem in defining its path integral. To see this, we're going to discuss the path integral in Euclidean signature on a compact 1 manifold. Well, there's only one compact 1 manifold up to isomorphism. There it is. Only one compact connected 1 manifold. As Dennis, thank you, Dennis, for this clarification. But there are two spin structures on this 1 manifold because lambda may be periodic or anti-periodic in going around the circle. So in string theory, these would be called the Raymond and the Rochefort spin structures, corresponding to periodic and anti-periodic. In the periodic or Raymond spin structure, lambda has a single zero mode. Namely, well, the Dirac equation, which you deduce from this Lagrangian, says just that d lambda dt is 0. So a solution of the Dirac equation is constant, but in case it's supposed to be anti-periodic, that forces lambda to be 0. And there's no global solution of the Dirac equation. But if lambda is supposed to be periodic, it can be a perfectly happy constant on the circle. So in the periodic spin structure, lambda has a single zero mode. Now, in path integrals, when you have a single fermion, well, we have n fermion zero modes, as we learned from 't Hooft in studying anomalies and instantons in QCD, you get an expectation value for the product of n fermion operators that soak up the zero modes. So if there's only one fermion zero mode, the path integral is trying to produce a non-zero value of the expectation value of lambda, which is a fermion operator. And such a non-zero value violates the symmetry -1 to the f, which counts fermions mod 2, the symmetry that's 1 for bosons and -1 for fermions. That's a symmetry that's important in physics in general and in string theory in particular. So a path integral that's trying to generate a non-zero value of a fermion operator is anomalous. It's inherently an anomaly. Related to this, though lambda has a one-dimensional space of zero modes, there's no natural choice of sign for the zero mode. So there's no way to make sense of what should be the sign of the non-zero matrix element, the expectation value of lambda. Any procedure that would tell us what the sign should be would explicitly violate the -1 to the f symmetry. That's obvious because the symmetry changes the sign of lambda, so any procedure that said that the expectation value of lambda is 3 or whatever would not respect the symmetry. So this is perhaps the simplest theory with an anomaly. However, it's important to know that in the Nevers-Schwarz spin structure, there's no problem with the path integral. First of all, there are no fermion zero modes, so there's no problem like that. But secondly, I can simply tell you the numerical value of the path integral. So if we go back to our Lagrangian, you discover that it was actually invariant under reparametrization of the circle. So see, this Dirac action in one dimensions only depends on the circle as a smooth manifold, really. So the path integral is supposed to be a number, not depending on anything. And the value of that number is the square root of 2. So if you want to know how to calculate that, well, one thing you could do is zeta function regularization, starting with the fact that the eigenvalues of the operator are n minus a half times a constant that depends on the radius. And then if you feed that into zeta function regularization, after a while, you'll get the answer square root of 2. Another way you can do it, more physical perhaps, is to consider two copies of the given theory with two fermion fields, lambda 1 and lambda 2. Thereby, we calculate the square of this path integral. And with two copies, there's no anomaly, and moreover, canonical quantization gives a rank 2 Clifford algebra, which leads to a two-dimensional Hilbert space H. And the path integral in the Nevers-Schwarz sector calculates the dimension of the Hilbert space, which is 2. So the square of our path integral was 2, so the path integral was the square root of 2. And that's a number that will be important later. Well, it's important later to compare with Sen, who got the same answer in a different way. Now, when we take an even number of copies of the original theory, then in the Riemann or periodic spin structure, there are an even number of zero modes, so there's no anomaly in -1 to the f. So that's why I call this a mod 2 anomaly. The odd number of copies of the theory has an anomaly, an even number of copies does not. So this is our first example of a mod 2 anomaly. A theory is anomalous, but the tensor product of an even number of copies of that theory is not anomalous. It has some unusual properties, but it's not anomalous. Yes?
How did you determine the sign of this?
Martin has asked an excellent question, which is whether the path integral in the Nevers-Schwarz sector could have been taken to be minus the square root of 2. So I've found that I have encountered no difficulties if I assert that for all circles, this path integral is the square root of 2. But I don't feel like I know a completely principled answer to your question. And I'm not absolutely sure there won't be a more subtle context where that sign will enter. Probably when we're doing unorientable two manifolds, unorientation reversing symmetries. The only answer I can give you is that I have not yet found a reason to look more deeply at that sign. I've worried about it, though, without finding such a reason. At the end of the lecture, we could think about it again and see if we can think of a better answer. But that will be my answer for now.
So it's also ambiguous when you use the zeta function?
Well, zeta function regularization in general gives a positive number, roughly speaking. Zeta function regularization, you usually take positive eigenvalues. And okay. I declared that the eigenvalues were n minus a half. You could have asked me why I didn't claim that they were minus n minus half. And then we would have found we had to discuss an eta invariant in order to determine this phase. I prefer to stick with the answer I gave Martin. There might be something that should be looked at more deeply here, but for right now, we're not going to. Now, for our second example of a mod 2 anomaly, we're going to start in 2 dimensions. And we're going to study a 2-component Majorana fermion in 2 dimensions. So if you don't know the jargon, the group spin 2 has a 2-dimensional real representation. So we are studying a fermion that is a 2-component real object. It lives in the 2-dimensional real representation of spin 2. And to write a Dirac operator for it, we need a pair of gamma matrices, and they will be 2 by 2 matrices, since the spin 2 representation is 2-dimensional, and we can pick them to be real 2 by 2 matrices. And when we do that, the Dirac operator is a real skew Hermitian operator. If you like your Dirac operators to be Hermitian, you could multiply by I and then call it an imaginary Hermitian operator. But I'll leave it as a real skew Hermitian operator. Now, the path integral of a single Majorana fermion is then formally the Pfaffian of this real skew Hermitian operator. Sometimes people call it the square root of the determinant, but more canonically it's a Pfaffian, and that puts you in the better mood for the fact that its sign does depend on an orientation convention. Somewhat analogous to what Martin asked about, except that in this case there really is an issue. So the Pfaffian of a real skew Hermitian operator, skew symmetric operator, is naturally real, but there's potentially a subtlety about its sign. Mathematicians would say that there's a real index bundle of the Dirac operator, and that this Pfaffian naturally takes values there rather than being a real number. To get a theory that has no subtlety in bulk, we can consider a pair of identical real Majorana fermions. So whenever I discuss an anomaly, I want it to be an anomaly relative to... I want something to be well-defined, and then we'll tamper with it and make it not completely defined and compute an anomaly. But our starting point, which is well-defined and anomaly-free, will be 2 identical Majorana fermions. So the Pfaffian is then the square of this real number and is positive, making the theory manifestly anomaly-free. So now, however, we're going to go to a Riemann surface with boundary, like I've drawn. And now we want to keep the fact that the Dirac operator is skew symmetric and real, so we want a real skew symmetric boundary condition. And there are 2 that are usually used in D-brane physics and actually more or less anywhere else that people discuss local boundary conditions on the Dirac operator. If n is the normal if n is the normal vector to the boundary, then you say that gamma dot n, Clifford multiplication by n, on psi is plus or minus psi along the boundary, with some choice of the sign. So these are 2 possible boundary conditions, and they're equally good because they actually are exchanged by a chiral rotation of psi. If you conjugate psi to gamma bar psi, where gamma bar is the product of the 2 gamma matrices. In other words, gamma bar is the non-trivial anti-central element in the Clifford algebra, the one that distinguishes the 2 chiralities in physics language. Anyway, there's a chiral rotation that flips the 2 boundary conditions, exchanges the 2 boundary conditions. So in the abstract, they're completely isomorphic, and it doesn't matter which one you pick. Now, I'd like to have a completely anomaly-free theory on a 2-manifold with boundary. Well, if I take a pair of Majorana fermions and give them each the same boundary condition on all boundary components, they're completely identical, then just as if there wasn't a boundary, this is a totally anomaly-free theory. The Dirac operator, we picked a boundary condition that preserved the fact that the Dirac operator was a real skew symmetric operator, so its Pfaffian is still naturally real, and the square of the Pfaffian is positive, telling us that this is a completely anomaly-free theory. We'll change things and get anomalies, but this theory is completely anomaly-free. A pair of Majorana fermions with completely identical skew Hermitian Dirac operators and boundary conditions. That's a completely trouble-free theory. The path integral is still the square of the Pfaffian, and it's still positive and anomaly-free. However, if we're looking for trouble, we could flip the boundary condition for one of the two Majorana fermions, or on one or more of the boundary components. So I drew a picture with one boundary component, but we could have a Riemann surface with many boundary components. And as long as the boundary conditions were the same on each, no matter what it was, this theory was trivially anomaly-free, because the path integral was the square of two identical Pfaffians. Now, however, on one or maybe more boundary conditions, we'll take the two Majorana fermions to have opposite boundary conditions. If we do that, then we get an anomalous theory, which in a sense has the same anomaly as before. I'm going to give two ways to see this. One is that we can take the theory with the flipped boundary condition on one boundary and compactify it to get the same anomalous one-dimensional theory we had before. So here I've drawn an annulus. My Riemann surface with boundary is this annulus. It's got two boundary components on the right and on the left. There are two Majorana fermions living on it. The right boundary has been labeled unflipped. That means that the two fermions have the same boundary conditions there. The left boundary has been labeled flipped. That means on the left, the boundary conditions are opposite for the two fermions. Now, I haven't completely specified the problem because I didn't describe the spin structure on the annulus, but whatever we do, if you solve a one-dimensional Dirac equation from left to right, one fermion will have a zero mode and one will not, because they obey opposite conditions at the two ends. For one of them, you'll have a minus sign problem when you try to find, if x is the coordinate that goes from left to right, if you look for a mode of the Dirac equation, the annulus has a flat metric, so it makes sense to say that a fermion is constant relative to that metric. If you want to look for a constant mode that satisfies the boundary condition on the left and on the right, that'll work for one of the two fermions and not for the other because of the way the boundary conditions were flipped. So solving the Dirac equation from left to right, you'll get one zero mode, and then going around the circle, the effective field theory in one dimension has a single real fermion. So we found that we could compactify this theory from 2 to 1 dimensions and reduce it to the anomalous theory we had at the beginning. So clearly, the flipping the boundary condition on the left boundary has created an anomaly. Now I'm going to give another explanation of that. I'm going to give another explanation that's related to developments in condensed matter physics in the Kitaev spin chain. So if we're interested in applications eventually to string theory, our fermions are going to be massless, and indeed I've written massless Dirac operators until this point. But if we're studying anomalies, anomalies are independent of masses, and we can turn on masses and try to simplify the study of anomalies. And if there were no boundary, the ability to turn on masses would actually be another way to prove that there was no anomaly. Well, I cut a corner in that statement. Well, I'm going to cut a couple corners. We'll see if anybody catches me. So I add a fermion bare mass, so the Dirac equation looks like this. And the point is that I can turn on bare masses without creating any anomalies that weren't there before, because in general, anomalies are independent of bare masses. A fancy math way to say it is that anomalies have to do with the Pfaffian line bundle, and that doesn't depend on your particle masses. It only depends on the leading symbol of the Dirac operator. A more physical way to say it is that if you knew what the path integral is supposed to be for zero mass, then differentiating with respect to the mass, you would just see correlation functions. So in general, the anomaly is independent of the mass, and we can try to calculate it when the mass is non-zero. And once it's non-zero, you can think of it as being big. So could we push our problems all away by making all the modes massive? Well, in the absence of a boundary, yes, but in the presence of a boundary, not quite. So we're going to look at this massive Dirac equation on a half space where x1 is non-negative, and look for a zero mode that's localized along the boundary. So in bulk, the operator d/plus m does not have an interesting kernel. D slash might have a kernel, but M does not. But we're going to see if we have an interesting kernel of the operator D slash plus M localized near the boundary. So I work on a half space where x1 is non-negative, and I try to solve the Dirac equation with a solution that depends only on x1 and moreover is localized near x1 equals 0. So I look for a mode independent of x2, and setting x equals x1, the Dirac equation reduces to this. And then we solve it, well, as done in a slightly different context a long time ago by Jakiv and Rebbe. And we get that explicit answer, but we want to know whether it's exponentially decaying or exponentially increasing as we go away from the boundary. Well, if the boundary condition was that, remember, our boundary condition was that the normal Clifford multiplication on psi was plus or minus psi. So that means in this notation, gamma 1 psi is plus or minus psi, where I've called the sign epsilon. So if gamma 1 psi, well, psi of x is something times psi of 0, and gamma 1 on psi of 0 is plus or minus psi of 0. So the solution more explicitly is like so. And you see it's exponentially decaying if m epsilon is positive, otherwise it's exponentially growing. So if m epsilon is positive, the attempt to trivialize the theory by creating masses has failed, because there's a mode along the boundary that will behave like a massless mode in one dimension, only propagating along the boundary. If m epsilon is negative, then the attempt to trivialize the theory has succeeded. Well, suppose we have two Miranda fermions. We give them masses of the same sign, ensuring that the bulk path integral is positive and describes a trivial gap theory at long distances. If the two fermions in bulk have masses of opposite sign, something funny will happen that we get to later. But we'll take the bulk masses to have the same sign. And so the importance of that is that the path integral is positive because it's a square. And well, a condensed matter physicist would say that for large m, the theory is gapped, and integrating out the gapped fermions only produces local non-universal terms that aren't interesting at long distances. So in particular, there's no anomaly associated to that. So if the boundary condition is unflipped, both fermions have the same sign of epsilon, and there are either two localized zero modes along the boundary or none, which in either case is an anomaly-free theory, because, as we learned, the boundary anomaly is a mod 2 anomaly. In the flipped case, one of the fermions has epsilon equals 1, one has epsilon equals minus 1. So regardless of the sign of m, one of them has epsilon m positive, one has epsilon m negative. So there is one localized zero mode along the boundary until we get an anomalous boundary theory. So I've now explained in two ways that flipping the boundary condition for one fermion creates these anomaly of the purely one-dimensional theory on that boundary. One argument involved the annulus, where we sort of globally solved the Dirac equation and compactified from 2 dimensions to an anomalous theory in 1 dimension, showing that there must have been an anomaly in 2 dimensions. In the second computation, we turned on a mass, localizing the anomaly along the boundary, and computing it explicitly, finding the mode responsible for the effective anomalous theory in 1 dimension. Any question on any of that before I go on to the third anomalous theory?
I have a stupid question. Is there a sense in which a d-dimensional theory with an anomaly, the anomaly can be viewed as a d-minus one-dimensional theory without an anomaly?
It's more in the opposite direction. The d-dimensional theory with an anomaly might be well-defined on the boundary of a d plus 1 manifold.
Oh, there's a d plus 1 theory without an anomaly? Of which
There's a d plus 1, well, it's a little bit too much of a digression for my lecture, but there can be a theory in 1 dimension more, which is anomaly-free but topologically interesting, where your d-dimensional theory can appear on the boundary.
With an anomaly.
By itself, it abstractly has an anomaly, but when regarded as part of the boundary of a system of 1 dimension more, there's no anomaly. However,
I want to have a picture for it.
explaining that is too far afield for this lecture.
So why don't you put it on the lattice? Because the ketone chain is on the lattice, or the XY chain, whatever you call it.
We can illustrate this anomaly on the lattice. After all, one of my explanations was on an annulus, and the annulus can be latticized. For our application, it's really important that we can work on a general Riemann surface. And then, okay, we probably, with more work, could laticize it. But it would definitely be tough sledding. And I thought my explanations in the continuum were sufficiently clear that we didn't have to work so hard as to laticize it. I'm not sure what we'd understand better by latticizing it. Any other questions? Now, of course, the anomaly is really independent of M, as I emphasized when I introduced it. We used M as a device to compute the anomaly, in this case. By taking M large and localizing the interesting action on that low-energy mode that propagated along the boundary, we got an explicit way to see how flipping the boundary condition produced the anomaly that we'd have by a single real fermion on that boundary. In the string theory application, M will really be 0, but there will be the same anomaly. Turning on M is one way to make the anomaly obvious. I think it's worth mentioning that if we consider a Riemann surface with two boundary components, each with Riemann spin structure, and on each of which we flip the boundary condition to create an anomaly, then we get a theory with a relatively conventional gravitational anomaly, by which I mean there's a diffeomorphism that changes the sign of the path integral measure. So each of these circles has a fermion zero mode on it. You can make a diffeomorphism that exchanges the two circles, so it's trying to exchange the two fermions. And it will reverse the sign of the fermion path integral, since those two zero modes anti-commute. So that's our second construction with the mod 2 anomaly. Flipping the boundary condition for an odd number of Majorana fermions induces such an anomaly. Well, there's one more thing we can do that involves the same anomaly. Let's discuss physics on an oriented Riemann surface sigma without boundary. So an important fact is that there are two types of spin structure, even and odd. To make this distinction, we consider a fermion sigma on a fermion chi on sigma. However, now it will not be the real two-component fermion that we had before, but a complex one-component fermion that has definite chirality. That means that spin 2 is abelian and it's got two one-dimensional complex representations. We pick one of them. And now it's possible to write a Dirac action for this field. It's anti-symmetric by Fermi statistics. The canonical form of an anti-symmetric matrix looks like this, with a lot of 2x2 blocks. And of course, a 2x2 block means a pair of skew eigenvalues, A and minus A. But then there can be zero modes that are not necessarily paired. The number of zero modes can change only when one of the skew eigenvalues, A, B, and so on, becomes 0 or non-zero. And when this happens, the number of zero modes jumps by 2. So the number of zero modes, mod 2, is a topological invariant called the mod 2 index. And I'll call it Zeta. It's called the mod 2 index of the chiral Dirac operator. As an example, here's a Riemann surface of genus 1. You take a parallelogram and identify opposite sides. There are four spin structures where fermions either change sign or don't change sign under parallel transport from left to right or from top to bottom. And in the plus-plus case, there's a single zero mode, the constant mode, where chi is a constant in the coordinates given by the flat metric on the screen. And the other spin structures have no zero modes because the constant mode wouldn't have the right anti-periodicity. So the plus-plus spin structure has zeta equals 1, and the others have zeta equals 0. So on a Riemann surface without boundary, a spin structure has the mod 2 invariant minus 1 to the zeta. So that means that a theory with fermions on a closed-oriented Riemann surface can have a discrete theta angle, which is a factor of -1 to the zeta that we include in the path integral measure. But -1 to the zeta can't be defined as a topological invariant on a Riemann surface with boundary, because there isn't a satisfactory boundary condition on the chiral Dirac operator that you could use for that purpose. So earlier in the lecture, for the non-chiral two-component fermion field, we wrote down the two most widely used local boundary conditions, but they have no analog for this one-component chiral Dirac operator. And there is, in fact, no complex linear elliptic boundary condition for this problem. Local elliptic boundary condition. There's a simple topological obstruction. So it turns out that in trying to define -1 to the zeta on a Riemann surface with boundary, we run into the same mod 2 anomaly as before. Before explaining this, I'll note the following. In defining zeta, it didn't matter if we used positive chirality fermions or negative chirality fermions. They're just complex conjugates of each other. Complex conjugation reverses the fermion chirality in 2 dimensions, exchanging the two one-dimensional representations of the group spin 2. So positive and negative chirality fermions have the same number of zero modes, and the zero modes are simply complex conjugates of each other. To see that complex conjugation reverses the chirality, I've defined the operator that's 1 or -1 for fermions of positive or negative chirality. It's I times the product of the two gamma matrices, where we need the I so that gamma hat squared is +1. Since gamma 1 and gamma 2 are real, this operator is imaginary, so its sign is reversed by complex conjugation. Now let's consider a Majorana fermion psi on a closed-oriented two-manifold. So Majorana means we're back to the real two-component fermion. It had this nice action, and quantum mechanically it has got this discrete chiral symmetry that assigns the values 1 and -1 for fermions of positive and negative chirality. Quantum mechanically, the symmetry has an anomaly. It assigns the value, so in general, fermion anomalies are always carried by the zero modes. What it means to say that a fermion theory has an anomaly is that there's a symmetry of the classical action that doesn't preserve the path integral measure. However, the path integral measure for the non-zero modes is always invariant by an argument that goes back to, I guess, Etoft and Fujikawa. Basically, the fact that the action is invariant means that the non-zero modes are paired up in an invariant fashion under the symmetry. The non-zero modes are not necessarily paired, and that's where the anomaly comes in. So to check for an anomaly, you ask if the symmetry of the classical theory is also a symmetry of the measure for the zero modes. Well, this symmetry assigns the value -1 to every negative chirality zero mode, +1 to every positive chirality zero mode, so we don't care about those. So if there are S negative chirality modes, the zero modes measure transforms as -1 to the S, which is the same as -1 to the zeta, where zeta is the mod 2 reduction of S. In other words, the chiral rotation flips the value of the discrete theta angle. Now, suppose the fermion has a bare mass M. Then the chiral rotation isn't a classical symmetry. It flips the sign of M, but it's still going to flip the sign of the discrete theta angle. Since the discrete theta angle was discrete, its being flipped or not flipped can't depend on M. Now, at the quantum level, to make sure we know what we're talking about, it's better to start with a pair of Majorana fermions with the same sign of M. So that's our completely trivial anomaly-free theory where we know exactly what the path integral means, and it's positive. If the fermions have the same mass M, the path integral is manifestly positive, and at long distances it's completely trivial up to local non-universal terms. So integrating out a pair of massive fermions of the same mass gives a trivial theory at long distances. But if we made a chiral rotation so that one of the fermions has negative mass, well, we get the product of two Pfaffians, but one would have the opposite mass. And there also would be a factor of -1 to the zeta because of the anomaly. So we learned that the product of the two opposite Pfaffians is the same as -1 to the zeta. The whole product has got to be trivial. So, well, -1 to the zeta squared is 1. So triviality of this product means that the Fermion path integral cancels or equivalently duplicates the factor of -1 to the zeta. So on a two-manifold without boundary, the path integral of a pair of fermions with opposite sign masses is equal to -1 to the zeta modulo effects we don't care about at long distances. So we got that by saying that if the masses were the same, the theory was completely trivial. And then if we made a chiral rotation, it had to still be completely trivial, a chiral rotation of one of the two fermions. But the theory that had to be completely trivial was the fermion theory times this -1 to the zeta. So that tells us that the fermions with opposite masses are generating, or equivalently they're canceling, -1 to the zeta. Now recall that anomalies don't depend on masses, so a pair of fermions with opposite sign masses is anomaly-free. It's not trivial and uninteresting, but it's anomaly-free. I've just claimed that the pair of fermions with opposite masses has -1 to the zeta times uninteresting things for its path integral. And the statement that it's anomaly-free is completely consistent. -1 to the zeta is well-defined on a Riemann surface without boundary. So it can be the partition function of an anomaly-free theory. And when I say it's well-defined, that means it's anomaly-free. They're really synonyms here. Now let's consider the pair of fermions with opposite sign masses, but on a Riemann surface with boundary. We give the two fermions the same boundary condition to make sure there's still a no anomaly. But they continue to have opposite sign masses. So in bulk, they generate the same -1 to the zeta that I described. But on the boundary, because they have the same boundary condition but opposite sign masses, they have the opposite sign of m epsilon. So one has a boundary localized mode and one does not. So the boundary theory is anomalous, but the product of -1 to the zeta and this anomalous boundary theory must be anomaly-free, because we got it from a manifestly anomaly-free bulk theory. Remember, we started in bulk with the positive equal masses, a completely trivial theory. We change the sign of one mass. It becomes non-trivial, but it's still anomaly-free because anomalies are independent of the masses. And this manifestly anomaly-free theory has a -1 to the zeta in bulk and an anomalous fermion on the boundary. So we learned that that combination is anomaly-free. So the conclusion is that, oh, terrible. There's a misprint here, namely the word not is omitted. The conclusion is that although -1 to the zeta is not well-defined on a Riemann surface without boundary, sorry. No, okay, sorry. This was misread rather than misprinted. Sorry. So -1 to the zeta is well-defined on a Riemann surface without boundary, but on a Riemann surface with boundary, it has the same anomaly as a single real fermion mode lambda that propagates only on the boundary. So that sentence is actually true. I just misread it. It has the same anomaly as the anomalous boundary theory that we started with. So to conclude then, we've learned about three things that have the same anomaly: a single real boundary fermion, a single bulk Majorana fermion with a flipped boundary condition, and the factor of -1 to the zeta associated to the discrete theta angle of the bulk theory. Well, since all three of them have the same anomaly and it's a mod 2 anomaly, anomalies can cancel between any two of them, and we even arranged for that cancellation just now between number 1 and 3. Now, there's a fourth thing with the same anomaly that was important in my paper with Robert. I won't discuss it today, but it's the orientation bundle of moduli space. So now we're going to get to string theory. So we'll consider type 2 BA and type 2b and type 2a superstring theory. For type 2, on a Riemann surface without boundary, left and right moving worldsheet fermions see different spin structures in general, and this is extremely important in avoiding tachyons and getting space-time supersymmetry and for all kinds of reasons. Now, for example, for type 2b, if the left and right spin structures are the same, the fermion path integral is manifestly positive because there are an even number of worldsheet fermions leading to the 10th power of a Pfaffian. And since 10 is an even number, the 10th power of the Pfaffian is positive. So there's no anomaly in that case. Well, we need to be more careful, but we'll get the same conclusion for the superghosts and even on a more general spin manifold after working harder. That's if the left and right spin structures are the same. If the left and right spin structures are different, it's not so obvious there's no anomaly. It can be proved using the relation between anomalies in 2 dimensions and the eta invariant in 3 dimensions. It's actually much more subtle than anything in today's lecture, and we're not going to go in that direction. That's in some old papers. So for today, we won't worry about the important detail of how to define the fermion path integral when the left and right spin structures are unequal. In fact, for today, you could imagine they are equal. The part of the problem we're focusing on today is orthogonal to this important part of it that I just mentioned. For type 2a, the path integral measure is not just the product of the Pfaffians, like I said for type 2b. There's an extra factor of -1 to the zeta left, where zeta left is the mod 2 index of the left chiral Dirac operator. You could use zeta right instead of zeta left. You'd get an equivalent theory differing by a reflection in spacetime. Concretely, at the one-loop level, you can show that including a factor of -1 to the zeta left reverses the sign of the GSO projection for left movers without changing it for right movers. That's the standard distinction between type 2a and type 2b. So that's all I'm going to say about type 2a and type 2b in the absence of branes. So on a Riemann surface without boundary, for type 2b, the path integral we'll think of as a trivial positive path integral, although that hides the fact that the spin structures can be different. And for type 2a, it's that trivial positive integral corrected by a discrete theta angle, -1 to the zeta. Well, that's all we need to know about the path integral away from the boundary. Now we want to consider a brane. That means we want to define the theory on a Riemann surface with boundary with some sort of boundary condition. Let's start with type 2b. In the case of a D9 brane, all worldsheet fermions obey the same boundary conditions with the same sign. The difference between D9 and D9 bar is whether the sign is plus or minus. So if you're not a string theorist and you don't know what a D9 brane is, it's just the obvious case where all the fermions have the same boundary condition. And string theorists consider both boundary conditions and call them D9 and D9 bar. Now suppose you want to describe a DP brane. Well, that means you want to flip the boundary condition for 9 minus p fermions. If 9 minus p is even, this introduces no anomaly, and we get the usual supersymmetric DP branes, where p is any odd number, so that 9 minus p is even. If 9 minus p is odd, flipping the boundary condition for that many fermions introduces an anomaly. But we know how to cancel it. We add a real fermion lambda that only propagates on the boundary. And I claim that this gives the non-supersymmetric type 2b DP branes of Sen with even p. We'll return to them later. But first, let's consider type 2a. Now we're in the opposite situation. If we try to make a D9 brane, since the fermions all satisfy the same boundary condition, they introduce no anomaly. But we have a problem anyway because there's a bulk factor -1 to the zeta, and this has an anomaly on a Riemann surface with boundary. So what are we going to do about it? To cancel the anomaly, one way is to flip the sign of the boundary condition for an odd number of bulk fermions. That gives a dp brane where 9 minus p is odd, so p is even. These are the usual supersymmetric type 2a dp branes with even p. But there's something else we could have done. If we want a dp brane with odd p, then flipping the sign of 9 minus p worldsheet fermions didn't help. But we can cancel the anomaly by adding a real fermion lambda that only propagates on the boundary. And that gives Sen's non-supersymmetric dp branes of type 2a with p odd. Yes, Natty?
Related by T-duality?
They can be, yeah. If you compact, well, T-duality was part of Sen's story, so it's still going to be true here. So what Natty asked was, yeah, okay. If we compactify in a circle that's contained in one of the branes and make T-duality, it'll exchange supersymmetric branes of type 2a with supersymmetric branes of type 2b, and it will likewise exchange non-supersymmetric branes of type 2a with non-supersymmetric branes of type 2b. I think it's fair to say that that's part of Sen's story.
You could have added any odd number of fermions.
We could have.
But
And
that doesn't happen.
it doesn't, well, I think the question, we could have, so the question was, could we have added, for example, when there was an anomaly, could we have added 3 boundary fermions? I believe the question is whether that gives something essentially different than adding 1 boundary fermion with also Chan-Paton factors. I believe we can do that, but it doesn't give anything essentially new. When we get to type 1, though, there are cases where you want to add more than 1 boundary fermion. I don't fully understand the whole story. Now let's discuss the physics of these non-supersymmetric branes. We can quickly reproduce many of Sen's properties. First is the brane tension. The brane tension comes from a path integral on a disk. The path integral on a disk of a non-supersymmetric dp brane of type 2a, the bulk part of the path integral is the same as the corresponding path integral for a supersymmetric dp brane of type 2b. But in the non-supersymmetric case, we have a boundary fermion. And as I told you at the beginning, its path integral is the square root of 2. So, as Sen discovered, the non-supersymmetric dp brane tension is the square root of 2 times bigger than that of a supersymmetric brane of the same p that would exist in the opposite string theory. That's one of Sen's results. So, Sen had the square root of 2. Now we can consider vertex operators. What sort of vertex operator V can we insert on a boundary of the string worldsheet associated to a non-supersymmetric brane? So here's the worldsheet, and here's a boundary point. We're inserting an operator V. What can V be? Well, usually V is a superconformal primary of appropriate dimension constructed from all the available fields. In addition, it's usually constrained to be GSO even. So GSO symmetry is a discrete symmetry that decides whether the operator is bosonic or fermionic, and only one is allowed. In the case of a non-supersymmetric brane, we also have the dimension 0 fermion field lambda that's defined only on the boundary. So if V is GSO odd, then lambda V is GSO even, because lambda itself is GSO odd. So that means if you don't explicitly take lambda into account, you'd say there's no GSO projection. For every vertex operator V, either V or lambda V is GSO even. And so every superconformal primary made from the matter fields corresponds to an allowed vertex operator. That's also part of Sen's story. Finally, there's also a selection rule for the insertion of GSO odd vertex operators. Well, remember, a GSO odd vertex operator is a GSO even vertex operator that is of the form lambda V, where V is GSO odd. So when I say the operator is GSO odd, I mean the conventional part of the operator is GSO odd. So the statement we want to make depends on whether lambda has a zero mode. On a boundary component where the spin structure is of Nevers-Schwarz type, that means antiperiodic, lambda has no zero mode. So the number of, to get a non-zero path integral, we then need an even number of lambda insertions. So the number of GSO odd vertex operator insertions must be even on every such boundary. But on a circle in which the spin structure is of Riemann type, there's a lambda zero mode, and the number of GSO odd insertions must be odd. This is true separately for each boundary of a Riemann surface. I've drawn it as if there's only one boundary, but if there are many, this selection rule applies on each boundary separately. And this is again part of Sen's story. Now, because there's no GSO projection on a non-supersymmetric type 2 DP brane, the non-supersymmetric DP branes of type 2A and type 2B are all tachyonic. There's always a tachyon vertex operator in the DP-DP sector. And Sen explained, well, heuristically and also in string field theory, how that can lead to flow to a supersymmetric DP-1 brane. If I write the usual GSO odd tachyon vertex operator, well, if I write the top component this way, the GSO even tachyon vertex operator is this one. And so we always have that GSO even tachyon vertex operator for type 2B. Now, Sen also constructed non-supersymmetric DP branes for type 1, where he focused on the cases where P was 0 and -1, and showed that those cases were important in understanding heterotic type 1 duality. So, moreover, these DP branes are non-tachyonic. Now, non-supersymmetric DP branes exist in type 1 for both even and odd P. What I've explained is most simply applicable if P is even. So let's discuss that case. But Eric had asked me if it's interesting to put more than one boundary fermion. So for P odd, it's useful to put two boundary fermions. So that's the case I know where it's useful, but I don't know for sure about other cases. So remembering that type 1 has various supersymmetric DP branes with odd P, to make a brane with even P, we'll need to include a real boundary fermion to cancel the anomaly we've been discussing. Equivalently, since type 1 descends from type 2B, and what I just wrote here is true for type 2B, it's also true for type 1. We need an odd number. That's the case where we need an odd number, well, a real boundary fermion, or in general an odd number, to cancel the anomaly. There will also be a Chan-Paton bundle on the brane. For type 2, it would be a unitary gauge group, but for type 1, it will be orthogonal or symplectic when P is even, and we'd like to decide which one. There's actually a quick way to decide which one, which is to look at the DP D9 strings and ask that they should be real. And then that tells you, well, you have to modify the argument if P is -1, but if P is bigger, the fermions are spinors of spin 1P that are also bifundamentals of G times SO32. So a certain tensor product has to be real. And you learn that the answer that the Chan-Paton group is orthogonal for 2 and 8 and symplectic for 4 and 6. It's also orthogonal for 0, as Sen showed, by a variant of this argument. So most of these non-supersymmetric branes are tachyonic, except for the ones whose importance was identified by Sen. But sometimes, even when they're tachyonic, if you make an orbifold of the directions perpendicular to the brane, you can remove the tachyon. So there are some non-tachyonic constructions that go beyond what Sen actually described. So there isn't really time today to discuss the non-supersymmetric type 1D branes with odd P, which are D-1, D3, and D7. So I'll just remark that including a pair of boundary fermions helps clarify their properties. Thank you.
Other questions? Very naive. How does this work from the space-time point of view? Because we know the usual supersymmetric branes carry the charge of the appropriate Riemann fields. And the non-supersymmetric branes obviously can't because those fields aren't there.
No, they're neutral. Well, after all, okay. They're tachyonic, so they can decay, usually. I mean, Sen found some exceptions. There are a couple other exceptions in type 1. For type 2, they're tachyonic and they can decay. Something that Sen showed is that there's an interesting coupling of the gradient of the tachyon to a Riemann field of one less dimension on the brane. And that leads to the fact that a domain wall of the tachyon can carry brane charge. So Martin's question was this. In the supersymmetric case, there's a p+1 form that gets integrated over the world volume. If we take the non-supersymmetric brane, that means, well, what could we integrate over mp+1? There's no Riemann field of the appropriate degree. There's one of a degree 1 less. And then there's a coupling of that. This is type 2. There's a coupling of that to the gradient of the tachyon. And that has the interesting property, which Sen actually reminded me of by email the other day, but I think it's part of his story from 20 years ago. It has the interesting property that if the tachyon condenses with opposite signs at the two ends, a domain wall in between carries brane charge and is believed to decay to the supersymmetric brane, p-1 brane. Yes?
Is the fermion of the endpoint of the string related to the Goldstino?
You mean the space-time Goldstino?
Is it just the word line of the Goldstino?
Not in an obvious way, because for supersymmetric Goldstinos, there might be some context where the answer is yes, but it doesn't come immediately to mind. Because after all, supersymmetric Goldstinos arise in supersymmetric constructions. And this lecture was really about constructions that violate supersymmetry. I figured they fit into the theme of this workshop in Martin's honor because it all happened in a worldsheet supersymmetric theory that also has space-time supersymmetry. And it's even part of a worldsheet supersymmetric construction, although I didn't emphasize that in the lecture. But we discussed non-supersymmetric branes in a supersymmetric theory of geometrical interest.
The question is probably that the Goldstino is because of the bulk has supersymmetry.
Yeah, the brain has Goldstinos that are localized because the brain breaks supersymmetry spontaneously. So when the string moves on the brain, it could be the world line of that Goldstino.
So let's see. Okay. We have a non-supersymmetric brane. Well,
So there's a Goldstino.
I see, sorry. But it's not trapped as the endpoint of a string. And it's a space-time spinner. This fermion at the boundary of the string is trapped at the boundary of the string and it's neutral. But I wouldn't be astounded if in some context something like what you're saying turned out to be true. I can't offer a quick answer. Yes?
Related question. I mean, when we quantize the string that you have here,
Yes.
it gives us a space-time spectrum where this fermion was placed on both.
Well, let me discuss that. So, okay. I'll explain the analog. I explained it for vertex operators, but now I'll explain it for string states. We quantize the string. So there's stuff in between. There's a lambda at one end and there's a lambda prime at the other end. Then so let's first look at the action for lambda and lambda prime. We quantize it and we get a two-dimensional Hilbert space. Then we quantize the stuff and we get the usual string Hilbert space. Then we project onto the GSO invariant part. And you see, in this two-dimensional Hilbert space, one state is even, one is odd. So what survives the projection is H stuff even, tensored with the even part here, plus odd tensored with odd. So if you don't discuss the two-dimensional space, you would just say you decided not to make a GSO projection.
So it changes also the spin statistics. In this case.
No, the space-time spin statistics theorem is obeyed. But sometimes you'll get both chiralities of fermions.
In order for it to be obeyed, this lambda fermion did play a role.
Let's see. Probably. That must be right. I mean, lambda is a fermion. Sorry. In the right context, I'm sure you're right. I can't give the right answer. I've run into it in thinking about this. I just can't think of the right thing to say right now. I'm confident you land on your feet. Yes?
Do these branes carry any discrete charge that would not prevent them from decaying?
Well, in one, the question was, do these branes carry discrete charge? Generically, no, I don't believe, but there's a famous case where the answer is yes. That was for the type 1 D0 brane of Sen. which transforms in the spinner as a spinner under SO32, spin 32. And so it transforms non-trivially in the center of spin 32, which ordinary string states transform trivially. I don't know another example, but I'm not sure there isn't one. This subject has not been too much explored, so I wouldn't be too surprised if there are more surprises. But I don't know what they might be. Yes?
Very qualitative.
Yes.
So these are non-supersymmetric brains. You put on you have
Yeah.
Are there non-supersymmetric qualities all now explained in terms of these extra fermions, or are there additional things that can't be? Or is this somehow the essence of it, that there are these extra
Well, I believe that this explains the main peculiar properties of Sen's construction. But whether there's something I haven't thought of explaining that should be explained, I don't know. Well, in type 1, there's some details I don't understand.
Could
Okay.
you have had a non-supersymmetric brain without some odd fermion like this?
Well,
That's kind of a part.
as I explained, if you try to construct it, you run into an anomaly that you have to cancel somehow. So the question is more or less, can you think of an essentially different way to cancel it? I mean, I'm not absolutely sure there isn't anything else I can only say. I lectured about 3 things that have the same anomaly. There's a 4th, but it doesn't seem to be useful, that entered the other paper. But it doesn't seem useful for this application. Well, I don't know what I don't know. Any other questions?
Okay, if no more questions, let's thank everyone.